Hello everyone, welcome to the Bangalore Theory Seminar Series Talks. Today we are very excited to have Anay Mehrotra as our guest speaker. Anay is a fifth year PhD student at Yale University where he is advised by Professor Manolis Zampetakis and Professor Amin Karbasi. He studies machine learning algorithms in contexts where the data is corrupted due to structural errors, societal biases, and adversarial manipulations. In particular, his work designs algorithms with desirable properties like robustness, fairness, and efficiency. His work titled Towards Controlling Discrimination in Online Ad Auctions received the Best Student Paper Award at the Workshop on Mechanism Design for Social Good 2019. Today, he's very kindly agreed to give a talk titled Efficient Statistics with Unknown Truncation, Polynomial Time Algorithms Beyond Gaussians. And let join me in welcoming Anay and over to you.
Thank you. Can you hear me? Yeah, so I'll be talking about statistical inference with unknown truncation and some new algorithms for it that we developed with like Jane Lee and Manolis Zampetakis, who's my advisor. Okay. So that's the fairly standard outline of the talk. I'll give some motivations, preliminaries, and then hopefully get to some technical overviews and future work. So ML is a data-driven science. Developing good models requires having good data sets, where by a good data set, I mean a data set that is representative of the context in which ML model is deployed. The issue is that good data sets are hard to find, and many data sets that are used to train ML models in practice have some form of selection bias. And in today's talk, I'll be talking about two of these selection biases, truncation or censoring. So in truncation, what happens is from the whole data set, you only get to see some part of the data which falls in some set defined by various combinations of how you measure your data to how you collect it. And in censoring, it's the same as truncation, but you get to see how many samples are hidden. So at least the number of hidden samples are given to you. So I guess the takeaway is truncation is the harder of the two settings. So truncation is what I'll be focusing on. And both of these arise due to many reasons. Some of them are limitations of your measurement device. So you gather your data at the end through some device, at least in physical sciences. And all of these devices are finite precision. They have limited range of measurement and so on. And I'll give some more examples. But it's not just the issues with your measurement devices. Sometimes it's also data collection methods. So if you're training an image classifier, how do you source the images with which you train it? Are some countries more represented than others in their data? But more historically, these truncation issues have been studied in clinical studies or survey data in general, where you ask everyone to respond, but only some subset of people respond, and you don't actually get to see who responds. And a final reason is that even if you have collected the data, there might be legal, ethical, or policy constraints which limit you from using that data. Maybe you have to not add noise to it before you use it, or you have to set certain data apart. So because of all of these reasons, truncation and censoring are very common in physics, economics, clinical studies, and social sciences. And there's a huge work in statistics and econometrics trying to develop quote unquote algorithms for it. They design methods which are efficient in low dimensions, but yeah, don't really scale very well once we get to high dimensional regimes. And the broad area of the broad goal of this area and also of this talk is to design ML systems or algorithms so that I'll give some motivations. So the first is a setting in economics. This is one of the survey type of results. And so in the 50s and 70s, what people were trying to do is understand intelligence's effect on income, and in particular, income of low skill of workers who work in low skill jobs. Right? Obviously, in high skill jobs, you expect IQ, some notion of intelligence to be correlated with income, but is it also predictive in low skill jobs was the question they were interested in. And they instantiated intelligence as IQ, which is questionable, but that's what they went with. And low skill jobs as any workers who are paid let's say under 10 USD per hour, or whatever is the poverty limit right now. But how do you analyze such a question? And they chose this natural data collection approach. So you can't, like, one approach is to go out and gather this data, right? That's hard to do. But survey data of families is like readily available. Like whenever there's a census, this data is collected. And this is like for each family, their household income. And how do you identify low-skill workers or workers in low-skill jobs from this? One approach could just be to look at everyone whose family income is less than 1.5 times the poverty line. So that's the method they went with. And then you have certain dependent variables, which is the income, and you have covariates. So that could be IQ, but also you can also correct for training, education, what type of work they do, etc. And then you fit some regression model. In the simplest case, it's linear regression. That's what these guys did. But there's an issue in this data collection approach. It truncates potentially like intelligent workers who work in low skill jobs, but end up having incomes which are higher than 1.5 times the poverty line. And so that was some threshold that we arbitrarily chose to identify low skill workers, but it's also potentially truncating our data. And so this work was done in 50s and like 1971. And then a few years later, Hossman and Weiss realized this. And they developed a regression method which is sensitive to this like notion of truncation. And this is an extremely simple truncation. It's just like one threshold function for us. And they were able to show that they were able to debunk the previous studies and show that, okay, IQ does in fact have an effect. The previous studies was claiming that IQ has no or even a negative effect on income of people in low skill jobs. Yeah, this is one example. The properties I want you to take away from this is, in this case, the set of data which survives was known to us, and it was a very simple function, which is something I'll change in the next few examples. So a low skill job, yeah, they defined it as some job which is low paying. So a person working in a low skill job does not imply that they have an income, household income less than 1.5 times the poverty line. So the correction they employ is you can make a parametric assumption on what sort of density, let's say, your untruncated data should have, and you only get this like truncated data. And so instead of just fitting like least squares, you do something better than that. So yeah, how these people work is like they didn't do that classification. They sidestepped it to say by saying that everyone below the 1.5 times the poverty line is a low skill worker and unemployed, of course. So they don't classify like, so you have this data, which is a subset of all people who work in low skill jobs. And you can fit one linear regression line to it, which is just the least squares line. But there are other lines you can fit. And they change the algorithm which fits the line to it. They don't change the data as such. So you can do things like you can infer how many people are above the poverty line and what should, like, I guess I'll give you some ideas of what kind of solutions they came up with, because those will be simpler methods of the algorithm I like present in later. Okay. Any other questions? So the other example is in astronomy, and this is closer to the setting where we'll be dealing with, where sets are more complicated. And one of the examples is what is popularly called Manolis bias. So Manolis was the scientist who first identified this. And the bias is simple, right? As the same object gets further and further from the Earth, its light gets dimmer and dimmer. And at some point, your telescopes can't pick it up. So when you're conducting any survey of the sky, you miss out dimmer objects which are further away. So your truncation set looks something like this gray region. Like these are the kind of stars you don't see. And any inference you run on these stars is subject to some bias because of this, which you might want to correct. And again, the properties to take away are like, okay, what does the set look like here? It's slightly more complicated than a threshold function. It's a nice curve here, but like in practice, it's slightly more complicated because this curve is based on like your models of how light travels through like the atmosphere and so on, and there is errors in all of them. Right? So you should imagine the actual truncation set to be some noisy version of this. But even in astronomy, things are like more complicated. Like there are various other sources of truncation that's happening. And to explain that, I'll like give you this example of quasar detection. So quasars are very, very luminous objects which are like have this beam-like shape, and they're powered by a supermassive black hole at the center. But despite being very, very luminous, they're very hard to detect because they're typically very, very far away from the Earth. So their apparent luminosity is very low. Okay. And like one piece of, I guess, evidence to convince you is like we have been detecting stars and galaxies like since centuries ago, whereas quasars were first detected in 1960s. And even then it required a completely new method of radio astronomy to detect them. Like before that, everything was optical astronomy. And even when they were detected, we couldn't use optical telescopes to find them, like even confirm their observations till like the 90s when Hubble telescope and other like more accurate telescopes were put into orbit. So what is an example of a question that we might want to answer? We might want to understand like were older quasars brighter? And how can you answer this? You can look at the apparent luminosities of the quasars. You can plot the redshift on the x-axis. And as the redshift becomes larger and larger, the object is like further and further away and older in time, right? So if this scatter plot that I construct of quasars has a positive correlation, then that's sort of a yes answer to that question. Does that make sense? Was there a question? Okay. So that's correct. Like whatever I said was correct if you see all of the data or you see all of the quasars out there. But as like these dotted lines indicate, that's not quite the case. So there's various forms of because these things are hard to detect, there's various forms of truncation that's happening. So when you look at the lower curve, quasars which are very dim, their redshifts are very hard to detect. So astronomers typically drop them. There's a lot of noise in them. So that's the bottom region. Then quasars which are very bright are very hard to distinguish from stars. So to avoid like getting a lot of stars in your data set, they also truncate out the samples above that line above. And the third thing is that observing quasars is very costly. So typically the data sets you get are a patchwork of different like studies. So even in this data set, the reason so the reason this area is missing is because this was from a separate survey and this was from a separate survey. So there's like various sort of like weird truncations happening. And I guess the takeaway here is that the survival set is very complicated and it's only approximately known because these are all hand chosen limits, right? So yes, you chose things which are bright enough, but maybe there's still some error in the redshift and so on. Okay. And the final like piece of information here is that like if the survival set is very complex and I tell you nothing about what's outside, you can't really make any inferences. Like I can have a very like adversarially chosen set of examples outside which make it like not negative or not positively correlated. So you have to make some parametric assumptions on the density. But the nice thing is astronomers are okay with that. There are other ways for them to verify this parametric assumption on the density. So like you shouldn't imagine a Gaussian here, but like some more complex parametric density can be estimated. So I guess that was all of the motivation. If there are any questions, like it's worth asking. Otherwise, I'll like start defining the problem and get into the ideas. So yeah, I'll try to abstract this problem like cleanly and not to spend too much time on it. So there is some like parametric family that you assume your samples lie in. And here we work with exponential families. If you are aware of this is like a very pragmatic and like flexible family. It captures a lot of distributions out there. So it captures normal distributions, exponential distributions, like many other types of distributions you can come up with. And for the purposes of the talk, the only thing to you need to remember is like the density has roughly this form, where like you have some base measure, which doesn't depend on any parameters, and then you have your parameter, which is theta, and it only shows up in the exponent, and it's multiplied by some t of x, which is called its sufficient. So this is some polynomial, and we'll not need this too much, except that, yeah, I mean, there's some parameter we want to estimate, which will tell us the density. And yeah, so there is some parameter theta star, which is hidden from us, which we want to find out. There is a survival set S star. It's a subset of the domain you're working with. And the one assumption we'll make about S star right now is, so this is that it has at least a constant mass with respect to the right density. And this is the notation I use for it. It's slightly non-standard. This means the mass of S star under the distribution E theta star. Okay. But other than this mass assumption, I let this set be non-convex, like disjoint, like not even connected, like arbitrarily complex for now. We need some like control over it later. And then I guess what I've been talking about is we see truncated samples. So as an example, let's say this is the true distribution, the standard normal distribution. A truncation set, let's say, is the 0-1 interval. Then the samples I show you is this like truncated normal distribution. And the problem is to identify what is the like these 0 and 1 parameters, the right parameters. This is theta star for me. Yes.
This means that constant fraction of this.
Yeah. Yeah. So it could be 1%. And like one more notational note, this is what I use to like denote a truncated density. So if I had a like S star in the parameter list, it means I'm truncating to S star. Yes. Yeah. So we have reduced it to parametric estimation, but regression is often a special case of this. Right. So you can get your regression coefficients out of this. But yeah, that's the problem. I show you samples from this truncated density, and I want you to find a parameter so that like this TV distance is small between the density you estimate and the true density. And like even for regression, TV turns out to be the right thing to do. So if you have the TV bounds, then you have like the usual regression bounds that you get. And yeah, we'll work in the high dimensional regime. So the dimension of my data and parameters is much higher than like 1 by epsilon, which is the accuracy you need. And a final note, like the setting I'll be working in is where you don't know S star, or you approximately know S star. And like, yeah, I'm making an even extreme case where you don't have any information on S star. Can we still solve this problem? Okay. Yes, you can have a lower bound on it. Let's say it's a alpha lower bound. But all that scales up is eventually it will only scale up my running time, so it doesn't really matter too much. Okay. So yeah, the naive thing to do is like some sort of like fitting on the data you see, and if you have no truncation, that works very well. But if you have truncation, then it doesn't work as well. Like you get this distribution, which is very far from the actual distribution. So before, like there has been some recent like work from CS folks on this problem. Before going to that, I'll like present like some preliminaries which I'll need to explain that work. So one is just this notion of log likelihood. The specific form is not too important. If you have not seen this, this is one of the standard methods for parametric estimation in stats. Right? You look at this function. Again, the form doesn't really matter, but the key thing is, okay, let me come to it, is that the true parameter maximizes this log likelihood. And under like very mild conditions, this is the unique maximizer. Very mild conditions like your density is full dimensional and so on. Okay. The other nice thing about this log likelihood is that it's convex. And one way to see it is to compute its Hessian and see it's a covariance. And covariances are positive semi-definite. It's negative of a covariance, so it's concave. The other nice thing I'll need is to look at its expression of the gradient. And the nice thing is that the gradient only has expectations over some like samples, right? This is useful because like the log likelihood itself, if I write it out explicitly, will involve integrals which over S, which when it's a complex set are very hard to do in high dimensions. But we can still get a noisy estimate of its gradient. Like that was like the key idea in some works in from 2018. Okay. The other notion I'll need is this notion of polynomial approximability. And this is like a very frequently used tool in learning theory, and in particular, like in agnostic learning, and almost all efficient agnostic learning algorithms rely on this notion of polynomial approximability. So the definition is not too important for us. This is the idea. Like, let's say this black set function is the indicator of the set I want to estimate. I say it's approximable by a polynomial if I can write this, if there is some yellow polynomial which is very close to the indicator function. Right, and I don't really care about stuff like very far from the origin because my densities will place low mass there. And the way to formalize this is to just look at this like notion of distance between the indicator and the polynomial and take its expectation. Right? And yeah, the typical norms we'll be dealing with is the L1 and L2 norms. So P here we'll want to be 1 or 2 for us. So polynomial approximability is nice, but it's very hard to get bounds on it. And typically people get bounds on it through this notion of Gaussian surface area. And like I can't give you an intuition of why. These are like deep results in geometry. But I can give you an intuition of what Gaussian surface area is. So this set here has a large surface area. And Gaussian surface area is just the analog of the surface area where instead of the Lebesgue measure, you look at the standard Gaussian measure. And yeah, so this line here has a very small Gaussian surface area. And this is nice because and Gaussian surface area, I guess the notation is gamma S. Gamma S denotes the surface area of the set S. And the nice thing is this theorem by like Cleveland, Soto, and Servideo, which shows that if a set has bounded surface area, then you need like polynomial in the surface area degree to approximate it. So again, the definitions won't be useful for us. The only useful things are like area can be used to bound polynomial approximability, and polynomial approximability is very good, very useful to get efficient agnostic learning algorithms. Oh yeah, the dimension doesn't show up because dimension is implicit in the surface area. That's the nice thing. Even if you have like very high dimensional half spaces, you only need constant degree polynomials to approximate them. No. So you don't have a lower bound on the measure because as the set gets farther and farther or lower and lower mass on your density, I don't really care about approximating it. This expectation becomes smaller and smaller. So I'm fine with a worse approximation. Like, yeah, these are very like I didn't believe these results when I see them, but these are true. So like if you want to, let's say intersection of T half spaces, you can still approximate it with a constant Gaussian surface area if the number of half spaces you have is.
One surface, you mean the uniform distribution of S?
That's a function of S. So expectation with respect to some distribution you're interested in, and the difference of the polynomial and the indicator function. So this 1 sub S X is this black line. Yeah, and like yeah, as you can see from some years here, like these are like old bounds. Like so people have known them for a long time. They're like very widely used in learning theory. So those are all the preliminaries. Now I can present like some work which has been done on it. So as I mentioned, there's a huge stacks in economics literature, starting even from like before 1900s. And their approach was roughly to show that if you maximize the log likelihood, just the empirical log likelihood that you get from your samples, that's a good enough way of estimating your parameters. So they developed all this theory that I skipped past. Then in 2018, like Daskalakis and others came up with an algorithm which can do this efficiently. Right? So all of the previous methods, they were doing this in 1 or 2 dimensions. Daskalakis et al. Can do this in like poly d by epsilon time, where d is your dimension. And the sort of access they need to S is they need a membership oracle to S star. So given a point, you can tell me whether it's inside of S star and not inside of S star. And the Skalakis et al. Showed this just for the Gaussian distributions, and like some other people like Jane, who's one of the I guess, or Jane and Manolis, along with Andre, showed that you can do this for like many, but a broader set of family, which we are working with. Okay. And both of these papers use projected stochastic gradient descent to optimize the log likelihood. And this is where they use the fact that you can't write down the objective function of the log likelihood, but you can compute its stochastic gradient because it was just an expectation of something. I'll come to that. Yeah, that's the question we ask. Like, but they need to know, they need to have a membership oracle to SR, and it's like if you just give their method an approximate membership oracle in some sense, then it's harder. And there are some issues even in learning SR, which I'll come to. And there's one work which does like try to solve this problem of unknown SR, and this is like a Fox 2019 work with Manolis and like some other folks. The downsides are like one is their running time, right? So instead of poly d by epsilon, you now have d to the poly 1 by epsilon, which is very large, but it's still not brute force. Brute force would be something like 1 by epsilon to the d. It's much better than the brute force, but it's still a bad running time. And the other downside is that they only work for diagonal Gaussians. You know, even the covariance matrix of your Gaussian, that you can do. And they developed like some like new tools to do this. I won't get into those tools because we won't use them. And the other sort of work here is like a lower bound, which is an unfortunate result that like this like epsilon exponential and epsilon runtime is like necessary if you don't make any assumptions on your set. There are two questions here. One, can we like extend this Fox 19 paper's work to work with first like Gaussians with general covariance matrices, non-diagonal? And can we extend it beyond Gaussians? The second work is it's impossible to do estimation poly d by epsilon time for arbitrary S star. But if we look at some restricted classes like half spaces or something simple, can we get poly d by epsilon algorithms? Right. And intersections of half spaces here would be very interesting because like the sort of examples I show you, you can approximate a lot of sets by intersections of half spaces. And these are the two problems I guess I'll be trying to answer. Yes, so it answers this question for arbitrary S stars. But if you assume that your S star is a half space or something more structured, then the lower bound doesn't apply. Yeah. So with that, I'll just first give our main results and then get to like the outline and how we get to them. And first, I'll just give our main results in the context of Gaussian because those are the easiest to explain. So the first algorithm is of the following form. If you get truncated samples from this normal distribution where S star is not known to you, then in this much time, you can estimate parameters which are close in TV distance. And like an implicit assumption here is like, yes, you do need a bound on like the Gaussian surface area of your set. Because you need to know when to stop your algorithm. Are there any questions on this statement? Like the details are not too important. The other result is like polynomial time algorithms. So if you assume your S star is a half space or an axis aligned box, so this is a box which is aligned with axes, then you can estimate, you can find these parameters in poly d by epsilon time. And right now I only claim this result for Gaussians, but this is even interesting even for like diagonal Gaussians. Even for diagonal Gaussians, we didn't know how to do this in polynomial, poly d by epsilon time. Whereas here there was some prior work which at least does it for diagonal Gaussians. Okay. And then like the other results are similar, so I'll just like present a diagram instead of presenting the actual statements. So this is what I've shown you so far. There's this Fox 19 work. We generalize it to general Gaussians and then speed up their algorithms to specific S star. And the nice thing about this approach was that our algorithms did not depend on something which uh, on some family of polynomials which are Hermite polynomials, which their work heavily depends upon. Which Hermite polynomials form an orthonormal basis for Gaussians, and they very nice properties are known about them, which is why they're able to play with them a lot. And it's a natural approach, but it prohibits you from generalizing beyond Gaussians. Our approach is not based on Hermite polynomials, so we can get generalizations to certain exponential families. So I need some assumptions because if you don't have any assumptions on your exponential family, doing inference even without truncation is hard. So you need some assumptions to make it tractable. But we get sort of analogous algorithms. So there's a general algorithm which relies on some notion of polynomial approximability. And there's a speed up, but now the speed up only works for access aligned boxes. So we don't know how to get a faster poly d by epsilon algorithm for half spaces. That's like an open question. Yes. Yes, that is true. You can find similar orthonormal bases for other distributions, but a lot of computational methods have not been that developed for other bases. There is hope to do that, and someone can develop all the theory and do it. But given the current technique, that seemed hard. So I'm not claiming that that approach won't generalize. It's just hard to generalize. So in this talk, I'll be focusing on the Gaussian results because the other things are once you write the Gaussian density in the exponential form, they just follow sort of immediately from it. You need to do some more work, but they follow. So I'll focus on this, and I'll also among these, I'll focus on this algorithm more. So now coming to the outline, where I think we'll answer some of Anand's questions of why can't you just learn the set and do some method that the previous folks were doing. So I mean, something I've been stressing is the main challenge is S star is not known to us. And the way we overcome it is in two steps. One, we'll learn S star approximately. So I'll learn this squiggly set, black set. And this will take me some exponential time. An exponential epsilon polynomial in d time. And then using this squiggly set, I'll somehow recover my parameters in poly d by epsilon time. So let's first assume that somehow we can do this step, right? I'll come to why this is challenging and how we do it. Then the issue is you have access to this squiggly set. If you just take the log likelihood and substitute S star by this set S that you came up with, the log likelihood doesn't make sense anymore. It's just infinity everywhere. Under very general conditions, it will just be infinity everywhere. So it's not informative. And I'll not talk too much about it, but what we do is just define some perturbed version of the likelihood, which is different from just substituting this S in the objective. And we can show two things for it. One, we can show that as long as S is close to S star, in the sense that the symmetric difference is small, the optimal of the new objective we come up with is close to the true parameter. So for the actual likelihood, you know that theta star is the optimizer. Now we don't know it's the optimizer, but it's close to the optimizer. And once you have both of these, you can use the projectic SGT method of previous works to optimize. Yeah, I won't be talking about this a lot because unless you're working on this very specific problem, the tools might not be of interest. I'll talk about this issue of learning S star. And the challenge here is that in typical learning theory problems, you're given positive and negative examples. So in this context, that would correspond to seeing stuff inside S star and seeing stuff outside S star. But that's our whole problem. We don't see stuff outside S star. And there are strong negative results from way back in the 1980s, which say that almost no hypothesis classes can be learned from just positive examples. And I'll be more precise what I mean by almost no. But one exception is axis aligned rectangles. or axial aligning boxes, which is why we are able to get a poly d by epsilon algorithm. So this is the challenge here, and how we overcome it is like we have some more information beyond just negative examples. We have some parametric assumptions on a density, whereas this result is for arbitrary densities. So yeah, we'll use that to overcome this impossibility result.
So here you're not assuming S star is convex line.
No, nothing. Yeah, I'll assume it's approximable with polynomials, but that's all.
Then I guess in general it would be exponential time learning it.
Yes. This I can't avoid usually. Yeah. Okay, and for the poly d by epsilon algorithm, all we do is like change this like algorithm for learning S star. So there are more efficient methods for learning simpler sets. Right? And for axis aligned boxes, as I hinted, like there is like folklore methods. You can find them in like ML textbooks. For half spaces, there are no such methods. Gaussian marginals. I'll not be talking about this. Like, yeah, I don't think I'll have time to talk about this, but I'll talk about the previous set of results. So, yeah, let's understand, I guess, why learning with positive examples is hard. So let's say the class we want to learn is circles. So I give you positive and negative examples. You want to identify the right circle that generated it. So let's say these blue dots is our underlying density is theta star. And this yellow set is the set that we want to learn. These are the positive and negative examples it generates. And if I give you these positive and negative set, there are like known algorithms. But I guess I don't show you the negative examples and I don't show you the set. So you only see these positive examples. And the question I want you to think about is, can you still identify the right set? Right. And the way I have structured this, like symmetrically, it's not the case. Like these other density of negative examples could also be the one generating these positive examples. And in that case, this purple set would be the right one. So you cannot distinguish between these two hypotheses, which are very far apart, from just positive examples. Like that's the essence of why this is hard. Like you can take this a step further and you can like question this. You can say that like I don't have to approximate the set by a circle, right? For instance, given these positive examples, if I just take this like this region, which is the intersection of two circles as the hypothesis I learned, then I seem to be able to identify it in this example. You can find the smallest like intersection of two circles, which has all the examples. But there are other examples you can come up with, which like violate it. So, and like, even if you look at like intersections of hypotheses in your class, I can come up with more examples. Like generically given a hypothesis class, there are counterexamples like this.
Yeah, Gaussian with me.
Yes.
That will be part of.
Exactly. Yeah. So like we'll use all of that. But that is just to say that like general learning theory tools which don't assume this can't directly be applied. We'll start using all of that. I guess I already mentioned this. Like there's a negative result which says a bunch of stuff can't be learned, but axis aligned rectangles are a counterexample. Okay. So one way to avoid this negative result, which is also something which is known, is you can learn with positive and unlabeled examples. So let's say you see these positive examples, but you also see these unlabeled examples. The rough idea is that like in this region, you can sort of infer that this must have been a negative example because you don't see anything positive around it. So if you had to choose between these two sets, you can say that we choose the yellow one because it like both of them capture all the positive examples and one of them has fewer negative examples. Right. And this is one like a formal program you can write for it. So the optimization problem you want to solve is minimize the number of unlabeled examples in your set subject to containing everything positive. Right. This can be shown to like learn S star if you have positive and unlabeled examples. And this was a theorem by Dennis in 1998. He didn't use this program. He used something else, but the result is similar. The result is that if you have positive and unlabeled examples, you can path learn, and the sample complexity to do that is the sample complexity of agnostic learning. So you're still paying something because this is a realizable problem. There's a hypothesis which currently classifies everything, and the sample complexity there is like 1 by epsilon typically, and you pay an epsilon squared. So you pay something, but you can learn everything that was learnable before. The problem is, in our setting, these unlabeled examples would correspond to E theta star. And if we had that, we can just estimate theta star directly. So we don't have that. Okay. Then how do we get past it? One idea was to come up with a distribution which is close to E theta star. So I won't get unlabeled samples from the actual underlying distribution, but something close to it. And the way I define closeness is I say theta 0 is close to theta star. If for any set t, like the mass of t assigned by theta star is sort of upper and lower bounded by the mass assigned by theta naught. Right. And like this is a very, very weak notion of approximating masses because the constant c you see here can be like 100 for us. Right? It's something which goes up with the mass of the fraction of samples you observe. If that c was 2, then this condition is equivalent to requiring that the chi-square divergence between these two distributions is constant. Right? So it's related to notions of divergence is known, but we'll only be able to guarantee like this very weak notion where like instead of a 2, we have like 100. Okay. And like I won't go into too much details, but like one question is how do you, yeah, sorry, you had a question? No. So one question is how do you find this theta naught? And finding theta naught turns out to be a simple problem, at least for Gaussian distributions. You just run like your typical MLE estimate on the truncated data. So if you remember, I showed you a truncated distribution, and I said if you take the naive method, you get something very far. But that thing which was very far from the two distributions still satisfies this notion of closeness. Yeah, I won't go into the like proof here. For Gaussians, at least, it's straightforward. Like you can just say that as long as any set has enough mass, it can't push the mean and covariance too far from the actual distribution. I'll skip this, and I'll get to like how we utilize such a result. Any questions so far? Okay. Then before giving the proof, I want to give an idea of how we use these positive and unlabeled examples. So this is our input, right? And now something that has changed is like earlier the negative examples were exactly from the circle the positive examples were from. Now it's like try to slightly change them. So that is just to say that I'm getting unlabeled samples from some other distribution. And the thing I do with it is very simple. I just convert all my unlabeled examples into negative examples. Now I have positive and negative examples. This is an agnostic learning problem. And my claim is any set which minimizes the error with respect to this distribution is very close. So like I get something like this. So the thing to note is like you have the symmetric difference between the sets you're interested in on the left-hand side. And at the right-hand side, you have the agnostic learning error and some like epsilon term. So if as epsilon goes to 0 and the agnostic learning error goes to 0, like your symmetric difference goes to 0. Make sense? T here. Oh, this is just to say that in agnostic learning, the error is never 0. So you take the difference of the error from the optimal hypothesis. So I'm minimizing over the, oh, here it should be S, sorry, that's a typo. This should be S. Okay. So yeah, that's our idea for learning S star. You first get samples from some distribution close to your actual distribution. You convert it into an agnostic learning problem, and then you want to solve it. Now, I'll give an idea of how this proof goes, but then I want to get to the question of how do you efficiently solve this problem. So this blue circle is our positive examples and negative and unlabeled examples, which I made negative. And these are negative examples. This is the right set. Suppose we came up with this set, right? It has a large error in this hashed out region. And I can identify that it has a large error in that region because it's positively classifying or it's including all of the negative examples there, which my yellow set is not. So that set has a higher error than my yellow set. Okay? So like it won't be the optimal for my agnostic learning problem. The other sort of set I can come up with is this one, which omits some positive examples. And here it's not clear whether it's like getting a larger error because it's omitting some positive examples, but it's also omitting some negative examples which are here. So the assumption I have to make is like you don't need to read it, but that the density of positive examples here is higher than of the negative examples, and then you pay an error here, right? This assumption is not really true for us, but we show that it's like almost always true. So in your domain, there can be a very small region where like negative unlabeled examples are more prevalent than positive examples. And all of this like immediately follows from this notion of closeness that we came up with. So again, I won't go through the proof here. It's essentially the same argument I gave in words. The other next problem, which is an issue for us, is to get an efficient algorithm for this agnostic learning problem. I mentioned that there are many like existing efficient agnostic learning algorithms, and all of them rely on some notion of polynomial approximability. And this is one general algorithm. It says that as long as, let's say you're trying to learn class S, as long as the class S can be approximated in L1 norm by polynomials, I can learn it efficiently. Right? And efficiently is again in this like epsilon time. So here L, which is the degree of polynomial, will typically be 1 by epsilon. So you still have exponential and epsilon time. But this is a conditional result. It says that for the class you're working with and the distribution you're interested in, you need to approximate the set by those polynomials. Right? The issue is almost all bounds and approximability are known for Gaussians or log concave or nice distributions like that. Whereas we created some new like problem by mixing two distributions, and this might be badly behaved. So in particular, we take some distribution of positive examples, which is truncated and looks like this blue line. We take a distribution of unlabeled examples, which we made negative, which is nice, which is Gaussian behaved, but their mixture is now like not nicely behaved. It's not log concave, it's not unimodal, in general, not nicely behaved. So to get an efficient algorithm, we still need to show that we can approximate like sets we are interested in with respect to this distribution now. And one way you might try to bypass it is to say that like both of the distributions I have in the mixture, so this blue and red one, they're nice. I can approximate S star, like there is some polynomial which approximates my set with respect to this blue density, and some polynomial which approximated with respect to the red density. Why can't I combine the two in some sense? The issue is that the polynomials can in general be very different. We don't have a good understanding of how these polynomials behave. So it's not as simple as, let's say, taking the average of these two polynomials to estimate it with respect to the mixture. Yeah, it's you need to assign a very large mass to the positive samples and very small mass to the unlabeled samples, and it's some polynomial function of epsilon.
It's dependent
Only on the error that you need. Yeah, I mean there might be constants which depend on various things. Okay, so the way we get past it is we show that there is a bridge distribution. So because like we came up with these red and blue densities, we chose them, and we proved that for Gaussians and for exponential families, we're interested, or some exponential families, there is always a bridging distribution that is like O1 distance in chi squared from both distributions. And it's the like nice thing to note here is that these two distributions I said were not close in chi-squared. They were close in some weaker notion. But still, we can come up with a distribution which is in between both of them in chi-squared. And we are able to prove such a result because chi-squared divergence is like non-symmetric. If it was symmetric, you have triangle inequality, you can never come up with something like this. Yeah, I'll come to that. Yes, you can. If you have, because we know the parameters of the red density, we can compute this. But we don't need to compute it anyhow, right? Because I need to show that my set can be approximated with respect to the green density, and I'll go through this black density to argue that. Okay. The argument is as follows. This black density is Gaussian. I can approximate my set with respect to it. That Gaussian density is close to both the red and blue one in chi-squared. And because of it, it's also close in to any mixture of them. It's close to the green one in particular. And then I can transfer polynomial approximability bounds. But there's a caveat here, which is, so this L1 regression algorithm, it has L1 in its name. It needs L1 approximation. L1 approximation of polynomials is a weaker notion than L2 approximation. And the nice thing is that Gaussian surface area gives us L2 approximations. So with respect to this black density, we have an L2 approximation, which is a stronger notion. And then it's close in chi-squared, and like because of this transferring from the black to the green density, we lose from L2 to L1. But that is still good enough for us. So there was this slack in previous results where they proved the results for L2 norm, but only use it in L1 norm, which we are able to exploit. And like, I only have 5 minutes left, so I'll just give an idea of the proof. It's very simple, like just this transfer result is very simple. It's just an application of the Holder's inequality. So this is the stuff you want to bound in L1 norm. You can write it out like this. You can split it up into two things, which are one, the chi-square distance between the distribution of interest and the bridge distribution, and L2 approximation. Yes, you lose a square root, but like, doesn't matter too much. So if you had epsilon approximability in L2 norm, you get square root of epsilon approximability in like L1 norm. So all of the talk, I'll just mention some future directions and then close. So like in the talk, I was talking about truncated statistic and like inference or regression with truncated statistics. And there are a lot of open problems here. So even just following up on our work, we gave a poly dy epsilon algorithm for half spaces, but intersections of half spaces, even two half spaces, is not known. And there have been like some developments in learning theory in learning intersections of half spaces. So there might be some hope to like transfer those tools to this setting. You can, when you want to do regression, if you have covariates which have like nicely behaved distributions like we have been talking about, Gaussians or exponential family, then you can use the tools we developed to do regression. But the problem of doing regression when you have non-Gaussian marginals, you have arbitrary data is open. We know how to do that with known truncation. With unknown truncation, this is an open problem. Like again, there is hope to solve the problem here. And the third problem, which I think like people haven't looked at, is estimating mixtures of truncated Gaussians. So you have two mixtures of Gaussians. There's some truncations that can you estimate, and this might be like a theoretically challenging problem, which like maybe requires you to combine tools from learning mixtures of Gaussians, which are like themselves very recent with some of the machinery developed here. But even beyond truncated statistics, there are many things to do. So truncated statistics can be generalized to this notion of covariate shift. So you had some distribution with respect to which you want to solve a problem. You like shift that distribution by some amount. That's called covariate shift. And then you do learning with respect to it. And like, yeah, we are trying to explore some generalizations of truncation there for learning. Yeah, for regression, Manolis has some recent work which does it, but for classification, it's like pretty open. Truncation or like these distribution shifts are like one notion of or one type of issue with data. There are many more types of issues. One of these types of issues is like coarsening or rounding, as we like in CS. are more familiar with. And it just arises due to the fact that like any instrument that you're using at the end has finite precision. And like I was mentioning, I mentioned that there are measurement issues and redshifts and so on. So typically, you only look at the first few bits of the redshift, right? So if you have such Gaussian data, can you still do like parameter inference with it? And for Gaussians, there's at least sample complexity known, and like we're trying to get polynomial time algorithms, and yeah, we have a polynomial algorithm for Gaussians for some notions of truncation, but like we're trying to extend. And this is also of interest for like econometrics. They call it friction. So they call it friction in my data, where like if you change my dependent variable slightly, my independent variable doesn't change immediately. So like also of some interest to other fields. And then there are some applications beyond learning theory and to causal inference. Causal inference is like is the field of study through which like you get vaccines, where clinical studies run. And the issue here is like very close to truncation, because they give vaccines out to certain people, placebos to other people, right? But for each person, you only get to see one of the two results. So if you could see both results for the same person, the inference problem or the learning problem here is very simple. But there's a truncation where for each person you see one, and like, they seem to get across it by making a lot of assumptions, which they can, in some cases, ensure in practice. But I think there's a lot of work to be done, like in like non-ideal cases there. Yeah, that's all. Thank you. If you have any questions, like I'm happy to take.
If we talk about what changes when we go to the general exponential families.
Yeah. So the main change you need is in estimating theta star, which is something I skipped deliberately because the tools change there a lot. So this method for learning the set S is very simple, is the same. But then so here, when you use projected stochastic gradient descent, the log likelihood now will look very different for these entities, but that's the only change. And like for Gaussians, I mentioned that there is this bridging distribution. You need to do some work to show that that exists. We only showed that for exponential distribution, so you need to do some work to show that it exists. To these like quasar detection type settings? No.
Sensor.
Oh yeah, so like censored setting is like you have more information there. You also get to see how many samples are hidden. So like all of these algorithms also work there. And like there has not been a separation between the two settings yet. Right. So there was this like old work in econometrics and stats, which relied a lot on, so this like first set of works, it differentiated between truncation and censoring a lot because their algorithms were handcrafted for the specific set S star that they had. So people cared about the differences between the two, but like, once we had this like Fox 2018 work, which showed that like essentially like all they need to assume about S star is that it has constant mass. Like it can be arbitrarily complex otherwise. So it's measurable, constant mass, but arbitrarily complex otherwise. Once you had that result, I think people care less about the difference. But in the unknown truncation setting, maybe you can get something better. Maybe you can get better algorithms or something, faster algorithms. I'm actually not sure if this lower bound applies when you have censored samples. So maybe you can bypass this. Yeah. Otherwise, like for the problems I mentioned, if you are interested in working on any of them, I'd be happy to talk. Thank you.
Thank the speaker again.
Small token of appreciation. Thank you.